Hello all, welcome to Samvaad Talks. I'm Shalini Singh, a student volunteer with IIITB Branding Committee, and I'll be introducing the speaker in the talk of the day. The topic of the talk is In-Band Full Duplex, a promising radio technology to double spectrum efficiency. And the speaker is Parthiban Annamalai, IIIT Bangalore, and Professor Debrata Das. Parthiban Annamalai is a PhD scholar in Networking and Communication Research Lab of IIIT Bangalore. He received his MS by Research from IIIT Bangalore in 2016. Currently, he is working as an architect in 4G and 5G DSP system engineering team of Modem R&D Group in Intel since 2015. His area of research include physical layer problems for 5G and beyond cellular system. Professor Debrata Das is Director Designate at IIITB starting 1st April 2021 and has been a professor at IIITB since December 2012. Before joining IIITB, he had served at GS Sanyal School of Telecommunication at IIT Kharagpur and later at Kirana Networks in New Jersey, USA. He is PIN Nodal Officer of project under National Mission of Interdisciplinary Cyber Physical Systems in the areas of Advanced Communication System from DST Government of India. He is PI of project from Tejas Networks on network node reliability. He was PI of multiple sponsored projects from Intel, HP, Microsoft, Motorola Research, Nokia Government of India on the areas of broadband, wireless, Mac, QoS, energy saving IMS. His main area of research includes IoT and wireless access, Mac QoS, power saving. Dr. Das has received his PhD from IIT Kharagpur. He has more than 170 peer-reviewed papers in different transaction journals and international conferences. Dr. Das has received 4 Best Paper Awards. He has 3 US and Indian patents and 12 more are under review. He and his wireless communication network team had contributed his ideas to IEEE wireless broadband standard. He has received Professor K. Srinivasan Memorial Award 2017 for excellent teaching in the areas of telecommunication from IETE. Professor Debrata Das is the PI and PD of recently awarded project under the National Mission of Interdisciplinary Cyber Physical System in the areas of advanced communication. Today's talk will discuss about in-band full duplex, a promising radio technology to double spectrum efficiency. Cellular networks are continuously evolving to facilitate many smart and connected applications. To support this growth, the International Telecommunication ITU and Third Generation Partnership Program 3GPP have come up with a list of enhancement items for future cellular system, of which improving data rate is primary enhancement item to support the unprecedented and growing demand for cellular data throughput. Considering that spectrum is a scarce resource, enhancing spectral efficiency is a recommended approach to achieve higher data rate. In IBFD is emerging as potential radio technology that can be achieved close to doubling SE. Before we start the talk, we thank our audience on both the platforms, Zoom webinar and YouTube. As we always take question at the end of the talk, so please feel free to leave question in the chat box as the talk progresses. Now, I'll request Parthiban sir to start the talk. Thank you.
Thank you, everyone, and welcome. Good afternoon, all. Welcome to this talk on in-band full duplex, the potential radio technology to double the spectral efficiency. And here is a rough agenda that I planned for today's talk. Let me start with the enhancement items, identified by the International Telecommunication Unit for the future wireless systems, and this is going to kind of set a stage for today's talk. And then I'll formally introduce this in-band full duplex technology. And after that, we will get into the details of the difficulties in the practical realization of this IBFD transceivers. And that will kind of result in the need for a hybrid network wherein only the base stations are full duplex capable, whereas the user equipments are going to be simply off duplex devices. And in this hybrid network scenario, there are 2 new types of interferences that are experienced. Let's get into the details of that. And more importantly, the resource allocation algorithms for this hybrid networks that would help us to achieve or maximize the spectral efficiency. And in this, as a part of this resource allocation algorithms, we propose, or there are works in the past also done about pairing or grouping UVs for frequency sharing. So that would help us to enhance the spectral efficiency. And then we will, summarize the learnings towards the end of this talk and as a closing remark, we will also, I plan to give some of the future challenges in this area, and yeah, we will have some time for Q&A as well. Okay, so this spider diagram on the right is probably familiar to many of us. So this diagram is from this International Telecommunication Unit vision document. Before getting into the details of this document, let's just see the typical use case scenario that kind of forms the basis for today's talk. As we know, the demand for the data throughput of a cellular network is exponentially increasing to support many smart and connected applications. You know, so in order to support this growth, there is a 1,000-fold increase in data traffic compared to the LTE, the 4G wireless communication standard. So this is what is foreseen. In order to meet this 1,000 times increase in the data throughput to meet whatever the kind of applications that are emerging these days, an obvious and straightforward approach is to allocate more and more spectrums so that this data rate can be achieved. And obviously, allocating a higher spectrum is a kind of linear approach, and we don't want to do it. Rather we wanted to go for an efficient techniques of increasing this data throughput without allocating the efficiencies in a linear fashion. So this is the aim of the today's talk. Now let's get into the details of this spider diagram. So compared to the 4G system, the ITU has come up with this spider diagram, which kind of portrays the different parameters that are to be expanded or improved upon, and they came up with 8 parameters. They are called as the KPI parameters, the key performance indicator parameters. Relevant to the today's talk would be the peak data rate. Obviously, we wanted to increase the peak data rate, as well as the user level data rate is also we wanted to increase. So at a system level, the requirement from ITU talks about 20 Gbps is the data rate for a future wireless system, and at a per UZ level, they wanted to achieve somewhere around 100 Mbps is the data rate per UZ. And in order to do that, of course, there are many ways that we can do it. And another important system parameter is spectral efficiency. So whatever the spectral efficiency that we achieved in LTE, the 4G systems, we wanted to achieve 3 times more spectral efficiency than what was there in LTE. Yeah, so we concentrate on these 3 parameters. And of course, there are other parameters like, we need to, the system has to, the future system has to support a mobility of up to 500 kilometers per hour. The latencies has to be less than 1 millisecond, and so on and so forth in terms of the connection density, energy efficiency, capacity, etc. But we wanted to concentrate on this data rate as well as the spectral efficiency of the system. So whatever the system design that we are going to come up, that has to be designed keeping these performance targets in mind. Okay, so we mentioned about increasing the throughput by by just not by allocating more and more spectrum. It's well known fact that the frequency spectrum is a very costly resource and also a naturally limited phenomenon. Okay, just to get a feel of how costly the spectrum is, let's get into some of this auction details from FCC. In Jan 2015 itself, 65 megahertz bandwidth has costed around a record-breaking 44.9 billion USD. And 5 years down the line, just recently in Jan 2021, another auction has exceeded to a limit of 80.9 billion USD is the cost of the spectrum. These factors illustrate how valuable the wireless spectrum has become. So it is inevitable that we have to start using this, developing efficient technologies, so that we don't consume more and more of this wireless. Yeah. So one of the recommended approach to transmit more and more data, but not to consume too much of frequency is the spectral efficiency. So spectral efficiency refers to the information rate that is transmitted over a given bandwidth, in a unit time. So it is measured in bits per second per hertz. So It means that the amount of information that can be transmitted in a unit time in a hertz, and that's what the spectral efficiency means. And obviously, higher the spectral efficiency is achieved, more and more information bits can be transmitted, of course, in the same spectrum. So that is the reason why improving spectral efficiency is a viable alternative method to achieve the required data rate, rather than going for allocating more and more the spectrum, which is anyhow very costly. Okay, so we understand that spectral efficiency will help us, in achieving the higher data rate. So what technologies can help us to, to really improve the spectral efficiency? One is this very famous MIMO. It's been there in since 4G onwards, the multi-user, multiple input and multiple output technology. It's a quite mature technology as of now. So this can definitely improve the spectral efficiency. And for example, if an n-cross n MIMO is implemented, we can easily get n-fold increase in the capacity. That's quite linear. However, reaching to this n-fold increase, I mean, we can't simply increase this n to any number. There are practical constraints. The antenna spacing between the spacing between the antennas, there are physical constraints. So it can't be less than the wavelength by 2, lambda by 2. So we have a limitation on this spacing of the antennas. Of course, maybe 4x4 MIMO is practicable. In base station, we can even go for a higher order MIMO, but user equipments like mobile devices, which are limited in size, we can't go for increasing the more and more antennas, as well as meeting this spacing limitations. So, of course, the MIMO can technically achieve the required or whatever the capacity that is possible, but there are practical limitations. We can't simply go on increase this step. So this is one of the limit. This is a primary limitation. Okay? On the other hand, NOMA is this non-orthogonal multiple access is another emerging technology that can also serve multiple UVs in the same frequency band at the same time. They are distinguished by different power levels. That's how the NOMA technique works. However, the resource allocation problem in NOMA is very challenging and also computationally intensive for higher number of units. So, in order to meet our performance targets of 3x, SC, there is no single technology that is available that would, help us to meet these targets. So we have to go in combination of one or more technologies, and these two emerging technologies, MIMO and NOMA, can really, do the job. But of course, there are limitations to that. So keeping these two techniques in mind, we will formally introduce the topic of today. It's called the in-band full duplex technology. Okay, so there's a famous statement from this book from this wireless communication book from Andrea Goldsmith. It states that it is generally not possible for radios to receive and transmit on the same frequency band because of the interference that it results. So today's communication systems are built based on this assumption, and it is an off duplex devices. It means that two different frequencies are required for transmission and reception. So that is how even the technology till date, including Wi-Fi or LTE or even part of the 5G that has evolved till now, they are also off duplex devices. So we need two different frequencies. I'm talking in the context of FDD, not in the context of TDD. So it requires two different frequencies for transmission and reception. However, IBFD is a potential technology that overcomes this long-standing limitation in wireless communication for more than 100 years, which has been, since then this wireless technology is evolving. So what it means is that this FD radios can transmit as well as receive on the same frequency at the same time. So that is the important feature of this IBFD. So the term IBFD and DFD can be interchangeably used. And since it transmits both it transmits as well as receives on the same frequency, it can achieve close to doubling the spectral efficiency. Whereas in an HD system, we are in need of two separate frequencies for transmission and reception. So since it can achieve close to double spectral efficiency, and it can manage with a single frequency, it alleviates the spectrum crunch that we have talked about, and also it has drawn a considerable research interest of late. So not only in the academic arena, even in the industry side also, the FD technique has become one of the hotspot regions, especially for 5G systems. And because of that, 5G is 3GPP, the standardization body for the cellular systems, has approved many study items on FD for its release 17 and release 18. Okay, so we have seen about how well or the advantages, the primary advantages in terms of the spectrum for IBFD. Of course, there are other motivations why we should go for an IBFD. So since it uses single frequency for transmission and reception, it can reduce the spectrum cost. That is one of the prime advantages. Moreover, when we are talking about the FDD, the frequency division duplex technology, it always we can just refer to this diagram on the right. It uses two bands of frequencies, a paired band of frequencies, one for uplink and one for downlink. So uplink is from an user equipment or a mobile to the eNode B or the base station, and downlink is from eNode B to the QA. So if you just, this is one of the LTE's band 13 example that I have given. The F1, which is used in uplink, can range from within this range. And similarly, there is a range defined for F2 as well. And there are many such bands that are defined. So what it means is that an FDD technology always requires a pairs of spectrum for UL and DL. And for the future system, again, if you wanted to design this, do this frequency allocation, we should always start looking for pairs of band. So that kind of puts the limitations on the flexibility. In case if you don't have a pair of spectrum, so this allocating more and more spectrum for FDD is becoming a difficult task. However, IBFD, as we saw earlier, it works, it transmits and receives in a same spectrum. So it means that it does not need a paired of spectrum, and it can very well work in an unpaired spectrum. Basically, a single band, we can allocate for both uplink and downlink. So this unpaired spectrum dramatically simplifies the spectrum management. Also, it increases the flexibility, and it's much more favorable for the operators as well. Moreover, since we don't have to look for a pair of bands always, since even any fragments of spectrum that are available, they can also be used by the operators. So that will also increase the pool of frequencies that are available for the communication. So the more and more frequencies will be available. So with these advantages, the cost of communication is going to be cheaper, and it is going to benefit regulators, operators, and consumers. So this is the motivation why this IBFD has become one of the stronghold research areas in recent days. Okay, so we mentioned about the advantages of FDFD. As we know, the systems have been developed or simply only half duplex compatible till date, and it's been like this for almost 100 years. There is a reason behind it. So practical realization of FD radio is not easy. If it would have been easy, maybe people would have already done it or realized it long before. So the prime reason here is that when when an FD radio transmits and receives on a same frequency, some of the transmit signal will be heard by its own receiver. Whatever it transmits, the same transmitted signal will get into its receiver. Generally, the transmit power is of the order of very high power levels, in the order of tens of dBs, whereas our received signal, the desired received signal, will be very less in power, maybe minus 110, minus 120 dBm. That is the order. So because of this huge power variations, there is the self-interference that we are calling the own signal that is reaching to the transmitter. It's called as a self-interference. That energy of the self-interference is generally a billions to trillions of times, which is like in a dB scale, it will be like more than 100 dB stronger than the desired receive signal. And if you wanted to realize an IBFD, yeah, we should be able to handle this self-interference properly. I've tried to put a simple analogy here, what an FD radio means. Yeah, trying to transmit and receive at the same time in a same channel is equivalent to trying to hear a whisper while shouting at top of your lungs. You know, our desired signal is of very low power level, which is being, suppressed by a very high strong interference. That is the reason why IBFD radios are not being practical so far. Let's get into the details of the self-interference. So we know that self-interference is nothing but whatever we are transmitting from the transmit side, that power is getting into our own receiver. So that is the self-interference. And this is caused because of the simultaneous transmission on a same frequency for both uplink and downlink, or for transmission and reception. So this is the self-interference is the primary reason why FD communication was believed to be infeasible so far. However, in recent years, many system designs and breakthrough technologies have emerged that has helped to suppress the self-interference before reaching to the receiver. So we don't have to completely cancel it. Yeah, there were techniques that has suppressed the self-interference to a decent level so that the communication is still possible. And if we could able to completely cancel the self-interference, a doubling of spectral efficiency can be achieved, since we use a single frequency for both transmission and reception. So in a practical system, the gain in the spectral efficiency is completely dependent on how well the self-interference can be suppressed before reaching its receiver. So it's all about, in an IBFD transceiver. So it is all boiling down to the factor of self-interference. That is what we need to address. Okay, so as we mentioned earlier, there are many proven works on IBFD so far. The very first promising work came from a set of 3 people from Stanford. They have developed a system, a practical system, wherein they've shown to achieve an SIC, self-interference cancellation of 110 dB of the cancellation. And this order of cancellation has helped them to, achieve throughput gain of 1.87 times over the traditional legacy of duplex system. Ideally, we should have loved to have 2x, but the cancellation of 110 dB has helped them to achieve 1.87 times of the hop duplex system. And this was achieved way back in 2013 itself. 2 years down the line, there were another work reported by a set of people here in the reference 3. So they managed to get they developed a prototype model for LTE itself, and that has achieved an SIC of 145 dB. This is much more than what Stanford people have achieved. And this 1.145 dB of SIC has helped them to, achieve a throughput gain of 1.9 times compared to the off-duplex systems. So these practical design circuits that has given the enough confidence, or for the people to feel that yes, this IBFD technique is practically possible now. Of course, there is a lot more work to be done, but there is a possibility that is emerging out. It's possible to design practical systems using the IBFD technology. Okay, let's get into some more technical details of this self-interference cancellation. Before going to this exact calculations, there will be a natural question, right? The self-interference is something that is coming from our own transmitter to our own receiver, which means we know what we are transmitting. So this natural question would be, since we know what is we are transmitting, why can't we simply cancel it by subtracting it from the received signal? This would be a natural question for anyone. So though it's not a simple one, as we can understand. So this cannot be simply eliminated because of the RF impairments. The transmit signal, before it reaches the receive part, it gets through this impairments on the RF impairments, both in the TX path as well as in the RX path. And moreover, there is a huge power difference that we have seen earlier also between the SI power as well as the received power. So these difficulties make it really difficult for canceling this SI. Let's take a practical examples to understand the numerics. In this example, I've taken a femto base station which can transmit at a power of plus 21 dBm, and its noise floor on the receive side is minus 100 dB. Okay, so on the right diagram, so the 21 dB is the transmit power from the base station, whereas on the base station receiver, the noise floor is minus 100 dBm. So what it means is that if this transmit power of 21 dBm, if it can be suppressed below the noise floor of minus 100 dBm, this self-interference is a negligible phenomena. And then the proper functioning of IBFD can be guaranteed. But so what is the order of magnitude of cancellation we needed? A plus 21 here, a minus 100. So it means that 121 dB of cancellation of the TX power is required. Only then it is possible to, it is possible to design a system without having any degrades in the receiver performance. So generally, we will see how this order of cancellations can be achieved. Let's start with an isolation factor. So generally at transmit antennas and receive antennas, there will be some kind of an isolation that is built in the antenna domain. Typically, people consider a 15 dB isolation between TX and RX antennas. So this will kind of bring down this 21 dB power to 6 dB. So even then, we need somewhere around 106 dB of cancellation after this isolation. Okay, and even this 106 dB is also not a simple amount. On this remaining two factors, let's go to the next slide and understand them. Yeah, let's get into the role of an AGC and ADC in a typical transceiver. So we know that AGC, tracks the incoming signal. It kind of automatically controls the gain according to the incoming signal. If the self-interference power is high and more dynamic range of the ADC is allocated for the SI, the self-interference power itself. And what it means is that the effective resolution available for the desired received signal becomes very less, because more and more dynamic range is given for the SI itself. Because AGC does not have a knowledge, it simply tracks whatever is the incoming power. Accordingly, it modifies the gain. Since the effective resolution of the received power is less because of this high SI power, generally, if the resolution is lost, the receiver performance also will come down. So what it means is that we can't simply cancel the self-interference in a digital domain, after ADC is done, because of this dynamic range problem. Okay, and a typical thumb rule for an ADC is that in terms of the dynamic range, a 6 dB per bit is a typical dynamic range for an ADC. So as a part of system design, generally we lay out to 2 bits for as a cushion margin, one for the clippings and other to prevent the quantization effects and stuff like that, and 1 bit is gone for a side bit. So even if you consider a 14-bit ADC, 3 bits are gone for as a cushion as well as for sign. What we are left with is only 11 effective bits. And with this 6 dB per bit calculation, 11 bits will lead to a 15.4 dB of dynamic range. Right? So if you come back to this diagram here, we had the incoming signal in the receiver of this femtocell receiver. It had a dynamic range of 106 dB, but our ADC, a 14-bit ADC, can provide a dynamic range of only 54 dB. There's still a gap of 52 dB. And see, all these calculations are specific to this particular parameters that we have considered. As we change the systems, as different parameters comes in, this numbers also will vary, obviously. So what it means is that it is simply impractical to take the entire self-interference to the digital domain and cancel it. Technically, maybe it is possible we can go for an higher bit ADC, maybe some 27-bit, 28-bit ADC, but which is simply not practical due to so many other constraints. So what it means is that we can't simply take the entire self-inference to the digital domain and cancel it. Rather than a multi-stage approach is generally followed. A multi-stage approach means that we have to do generally a three-stage approach is followed as per this work reported here. A propagation domain will do a part of cancellation in this propagation domain. The isolation part that we discussed between the TX and RX antenna comes here. And then there is an analog domain cancellation. This is in the RF domain. So we know what we are transmitting. We kind of tap some of the signals here and maybe implement a multi-tap and FIR kind of a filter and try to do whatever cancellation that is possible in the RF domain. So after doing a cancellation from the propagation domain as well as in the analog domain, then comes the ADC here. So this would have by then taken a significant portion of the SI suppressed. So we'll have only a portion of SI power that is left that can be handled. So in order to have a practical IBFD transceiver, it is required that a multi-stage cancellation approach one has to follow to bring this SI to the desired level, or more appropriately to bring it below the transceiver. Okay, so practical realization of IBFD transceivers involves intensive complexities at both here in the antenna domain, that is a propagation domain, as well as at the RF domain, as well as at the digital. So we need to evolve some high performing signal processing algorithms for this the residual cancellation, SA cancellation. So it involves complexities on all three domains. So what does it mean eventually? This will add up additional complexities in order to realize an full duplex capable transducers. So we know that our systems are already complex. If you wanted to accommodate these additional complexities, it's really going to be difficult, and these complexities will result in increased size and more cost, as well as it will start consuming more power. So in order to avoid that, a more practical approach would be to restrict this IBFD capability only to the base stations or the base. These base stations are less small in number, and also they are basically big in they can accommodate, because they're small in numbers. They can accommodate. There is no space constraint. There's no power constraints. Even cost is also it's not that of UEs, right? So we can afford to invest more there on the base stations, so that it is practical to bring this IBFD capability to the base stations. But for user equipment, it's simply it's simply not practicable in the near future. Moreover, we've seen that today's cellular UEs are only half duplex capable, and if you wanted to have full duplex capabilities, all of these off duplex today's user equipments, the mobile devices, have to be transitioned to a full duplex capable, which is going to be impractical in a limited time frame. So due to these reasons, it is realizing an IBFD transceivers for a base station is possible. For user equipment, it's simply not practical. So because of this reason, we are in need of something called a hybrid solution, okay, wherein what we do, the full duplex capability, we restrict only to the base station, whereas all these user equipments are treated as a normal legacy traditional off duplex today's off duplex device. So this would be a quite possible solution in the near future. And let's get into some of the details of this diagram. So we saw that this base station is a full duplex capable, whereas the user equipments are simply off duplex devices. And since base station is a full duplex capable, base station can transmit and receive on a same frequency, whereas this user equipments they require two different frequencies for transmission and reception. So in this system model, what we will do is that we will allocate a subchannel 1 for uplink of this UE as well as for the downlink of other UE. Since the base station is IBFD capable, he can manage it, he can transmit and receive. Whereas here we are ensuring that these frequencies, the user equipments are given two different frequencies. Similarly, there will be another, maybe a subchannel 3 that will be allocated for uplink of this user and downlink of this user. So in this system model, it is possible that so what we are ensuring is that we kind of introduce some kind of a frequency reuse that would help us to achieve higher spectral efficiency, as well as we are not touching anything on the legacy user equipment. And this is this frequency sharing is possible because of the IBFD capable full duplex. Now, the problem with this is that, yeah, this is practical, this is possible, but there is an associated problem with this. Since we are allocating an subchannel 1 for uplink of, maybe we'll call it as an UE1 here, and the same subchannel 1 is also allocated for an UE2, what happens when UE1 is transmitting on subchannel 1 in uplink, this uplink signal will come and cause an interference to this guy in its downlink, because this downlink frequency is same as this uplink frequency. And this is called as an inter-UE interference. And the same thing is applicable if you take an even other path. So yes, here it is subchannel 2 is allocated for this guy's uplink and this guy's downlink. And so this UV's uplink signal will come and interfere in the downlink of these other UV due to this frequency sharing. And if we can somehow manage this interference, this intra-UE interference between these UVs, then we can try to achieve the higher spectral efficiency that we wanted to achieve. Okay, so that is a part of the resource allocation in this hybrid networks. What it demands for is that today's cellular systems, as we saw, it is a half duplex compliant. It means that it requires one frequency for uplink and one frequency for a downlink, and all our resource allocation schemes of today's cellular technologies, that has been matured over decades, have to be redesigned. Now we have this problem. We have a system model is like that. The base station is IBFD capable, which can transmit and receive on a same frequency, whereas user equipments are legacy devices that requires two different frequencies. So because of this IBFD capability mismatch between the base stations and UVs, new set of resource allocation algorithms have to be evolved. That will replace this matured resource allocation algorithms that has been evolved over decades for the legacy systems. So as a part of this resource allocation algorithm, what we wanted to achieve is that we wanted to allocate optimal power and frequency for all UVs, such that if we just come back to this figure again, we wanted to allocate power as high as possible so that the coverage between the user equipment and the base station can be improved, as well as the link level performance is also better with a higher frequency. And moreover, if you start having an higher frequency, the interference that it creates to the other UE, which shares the same frequency, that also will go up. So if this guy is causing a higher interference to this guy, then this guy's downlink performance will be deteriorated. So on one hand, it is advantageous to increase the uplink power of this UE, whereas it has an adverse effect on the downlink of this guy. So we have to be very cautious on this. And moreover, this allocation is very important this allocation of frequency sharing between the UEs. So we will also do another frequency, as I mentioned earlier. This guy's uplink frequency will also be allocated as a downlink for this guy. So what happens in this case, instead of 4 frequencies that we were using in a legacy system, 2 for an uplink and downlink for this guy, and another 2 for uplink of downlink of this guy, we are managing with only 2 frequencies now. Yeah, so this sharing is inevitable to improve spectral efficiency. And also we need to improve the uh, power of uplink power of all the users to achieve a better range. But that also, so these two sharing mechanism and higher power has an adverse effect on the spectral, the interference. So the optimal allocation of power has to consider these three phenomena. So whatever I explained is what to put it in the text form. So what we have to do is that the joint allocation of power and frequency to be allocated to maximize the sum SC. That is a challenging task because of the factors that we. So one way it is advantageous to improve the TX power, otherwise, but it has an adverse effect on the interference. So an optimal allocation of power and frequency sharing is the need of the hour. And this allocation, this resource allocation problem for an HACM is already proven to be a NP hard problem. So many suboptimal solutions were proposed in. Okay, so we have seen the two kind of interference. One is the self-interference due to the TX power reaching its own receiver, and another one is the side-link in-band interference due to the frequency sharing. So these are the two different interferences that one is experiencing in this hybrid kind of IBFD cellular network that we need to address properly to maximize the benefits. Yeah, since we are restricting the IBFD capability only to the base station, we can afford to bring more complex system, more complex circuits, additional spacing between the antennas, all sort of possibilities we can afford to do it at the base station side. That would help us in a way to completely cancel the self-interference, because the restriction that we have on user equipments, mobile devices on the higher power, size, cost, so such restrictions are not much there on the base stations. So the SI cancellation on a base station is a realistic. So in that case, the challenging aspect in this HACN is restricted to only the side-link in-band interference between the UEs. So this becomes a performance bottleneck. And what does it depends on? Of course, it depends on the uplink transmit power from UEs, and more importantly, the distance separation between these two UEs. If these two UEs are sufficiently separated, then what we can do is that even if these two UEs are sharing the same frequency, the uplink power that this UE is transmitting before it reaches in the downlink of the other UV due to path loss and other phenomena, this would be attenuated sufficiently, and it will go below the noise floor of the cell. So if you ensure that this frequency sharing is happening only on a pair of UVs which are sufficiently separated in distance, this kind of a sharing mechanism is possible. That is applicable for any sharing that happens within this HACA kind of an. So that is what we have written here. So what I mean to say is that we can allocate one frequency for uplink of UE1 as well as for downlink of UE2, and another frequency for uplink of UE2 as well as to the downlink of UE1. And since these two UEs are sufficiently separated, UE2's uplink will not create any interference to UE1, as well as UE1 uplink will not create any interference to UE2. And this distance separation is we denote as a d-min, the minimum distance, such that this UV to interference, U to UV interference is kind of not perceivable, or it is attenuated below the noise level, noise floor, or also we can call it something like a sensitivity limit of a receiver. Okay, so the key element of such sharing is what we call it a QV pairing technique. So in a network with so many UVs that are being attached to a base station, how to find out the right set of UV pairs so that this kind of a frequency sharing is possible. So that is a important work on this work of this resource allocation. So in order to do that, generally the location aware selection. Since we know that only when we know the location of this UE, we can in a way guarantee that, okay, uplink power of one of the UEs will be sufficiently attenuated before reaching the other UE. So a location level selection is a recommended approach for these kind of hybrid networks in order to enable the frequency sharing. Okay, so let's get into the system model. So we have a base station. This is a IBFD capable base station, and these UEs are a typical legacy of duplex devices. And with the knowledge of the base station would get to know the location details of all the UEs. In fact, 3GPP has many positioning techniques available in 3GPP. So a base station can employ those techniques to obtain the location information of these UEs or all these UEs that are connected to a base station. And once it retrieves the location information, so in this Cartesian coordinate like X, Y, Z, it can identify their locations. And once this information is available, it the base station can find the inter-UV distances between these UVs. And once this inter-UV distance or the Euclidean distance between the UVs are known, based on this d-min value that we have discussed. So the d-min threshold is, and a computation of a d-min threshold is again a kind of an offline exercise that one has to do it. Okay, what would be the from simulations and for a given set of configuration parameters in simulations, we can run Monte Carlo simulations and try to find out, okay, what would be the minimum level of distance between a pair of UVs so that the self-interference, the sidling interference is minimized. So once we arrive at this d-min values, then a base station can identify a pair of UVs. Okay, if this Dij is greater than d-min, and UVi and UVj can be paired or and whatever the sharing mechanism that we've discussed, that can be employed. On top of this UV pairing technique, we have also introducing what is called as a grouping technique. So let's see here. Let's take a simplistic example of n is equal to 2, which means there are only two UVs, and the distance between the D12 is the equivalent distance between UE1 and UE2. If it is greater than or equal to this d-min threshold, then what we can do is that let's take an F1, the frequency 1, we can allocate for the uplink of UE1 as well as for the downlink of UE2, and take another frequency F2 that we will allocate to uplink of UE2 as well as for a downlink of UE1. In a legacy kind of an allocation, or if this distance is less than d-min, so we will fall back to our legacy approach, wherein F1 for uplink of UE1 and F2 for uplink of downlink of UE1, and F3 for uplink of UE2 and F4 for downlink of UE2. So it means that we need two frequencies for uplink for every UE for uplink and downlink. Whereas here, with only two frequencies, both the pair of UEs can be managed. So this is the concept of frequency, UE pairing. And this new concept of grouping, it enables more than two UVs to form as a group. So let's go back to this diagram. If Dij as well as Djk as well as Dki, if all these intra-UV distances are greater than the d-min, then all three UVs can form as a group. So if that is the case, this is an example allocation that we have given. Let's take F1. We will allocate to uplink of UE1 and downlink of UE3, and take another F2. We will give it to uplink of UE2 and downlink of UE1, and another F3 for uplink of UE3 and downlink of UE2. And in a legacy kind of an application, or if none of the distances are greater than the d-min, again, every UE, for example, it requires for uplink, it requires a UE frequency, and downlink also it requires a separate frequency. Similarly, for all the remaining two UA as well. So in this case, three UEs require 6 frequencies, whereas in this grouping mechanism, if this grouping is possible, then 3 UEs require only 3 frequencies. So what we've achieved here is that in spite of restricting the user equipments to legacy devices. So our user equipments are no longer full duplex capable due to whatever the limitations that we have discussed so far. In spite of that, we can still achieve almost double the spectral efficiency, uh, like a complete IBFD system where both user equipments are also IBFD capable as well as base station is also IBFD capable. So this is possible because of this intelligent grouping and pairing kind of techniques that are employed. So we have seen about 2 and 3, the number of UEs being 2 or 3. So how this can scale up for a higher number of UEs? Let's take this. So this is an example of N2 we have seen. This colors, just typically represent, pictorially represent a frequency. So one guy's uplink, other guy's downlink is the same. Similarly, this guy's downlink and this guy's uplink are the same. So it's just a pictorial representation of what we have seen. And this is exactly same for groups of 3 UVs. So this guy's uplink, this guy's downlink is the same, and this guy's uplink and this guy's downlink is the same, and this guy's uplink and this guy's downlink is the same. Whatever we have seen before, just a pictorial presentation. So this is for n is equal to 2 and n is equal to 3. If n is equal to 4, we can also do a similar, so we can have another bubble here. We can start doing the same thing. So this guy's uplink will be a downlink, and this guy's uplink will be a downlink. A straightforward extension of this, triplet grouping is also possible. And in a simplistic approach, we can just split them as split twins. Instead of making all 4 of them as a group, just split them as 2 twins. It means, so these 2 UVs will require 2 frequencies. These 2 UVs also will require 2 frequencies. This is equivalent to what we would have achieved if all 4 UVs are grouped as one group. Even then, we would have achieved 4 frequencies only. So that is managed with only groups of 2s also. So without any loss in the frequency sharing, rather than grouping all 4 UVs as a single group, if we can split them as pairs of 2s, even then the same performance can be, a performance of frequencies can sharing can be achieved. And similarly, if you wanted to go for in case of 5, we can form a group of 3 and a group of 2, right? So, and this approach can be extended for any number of UVs. So any, if you have odd number of UVs, see, provided all these distances are met, so we have to first extract the UVs that are eligible for frequency sharing, and then go ahead as a next step, we should go ahead and start doing the either the pairing or grouping approach, right? So all even number of eligible UVs, they can be split them as sets of 2s, and all odd number of UVs can be split them as one group of 3s and rest of them as 2 groups of 2s. Okay, so with this approach, it is this group, the pairing or the grouping approach can be extended to any number of UVs. So the challenge here is that we need to identify the right set of UV groups for the frequency sharing. So that is the challenge. So there is a lots of scope here in evolving multiple techniques in identifying such potential UV groups for the frequency sharing. So at the end of the day, what we wanted to achieve is that we wanted to bring more and more UVs into the groups such that the frequency sharing is possible. So more and more frequencies can be shared. That would help us to improve the spectral efficiency proportionally. In case if any one of the UVs is not part of the group, then that particular UV will follow this legacy approach, wherein we probably have to allocate 2 independent frequencies for its own ULNT. And so that would be the case. Probably, we can see a case 2 here. In this case, in this diagram, if only these 2 UVs are kind of meeting the constraints, and if this UV is not meeting a constraint, then if you can see that the 2 UVs form a pair, it requires only 2 frequencies. Whereas UV3, it requires again two different frequencies for its own transmission and reception. So everything now, whether a UE can share a frequency or it has to use two distinct frequencies for transmission and reception, it purely depends on these constraints that we have put in. We mentioned about only the distance constraint to kind of identify the eligible UVs for pairing or grouping, and it is also possible to impose more and more constraints at every UE level, to combat some random nature of the wireless channel, stuff like that. Uh, you know, so we can add more and more constraints to further strengthen this pairing or frequency sharing approach, so that this technique is robust enough for a typical cellular system. Okay, so that we are close to the end of this talk. So we have seen that full duplex is a very promising technology. It's exploits the spectrum, and with whatever the state-of-the-art cancellation techniques that we have seen so far, with the order of SIC that was achieved, it is highly practicable to deploy this full duplex on base stations, especially on small cell base stations, because the small station base stations transmit lesser power, so that the self interference in its receiver is also less. Accordingly, the self interference cancellation requirement is also less for a small cell base station. Whereas if you go for something like a macro kind of a base station, that would be transmitting somewhere around 45 plus 45 dBm. And if it's, for example, if it's a receiver sensitivity limit is somewhere around minus 120 dBm or so, we probably need somewhere around 160, 170 dB of SIC cancellation. Maybe we are not yet there to go to that level of cancellation. So since the small cells transmit less power, the SIC requirement for small cells is also less. So it's practical as of today to take it to take the IBFD for small cell base stations. And more importantly, the 5G also, the trend in 5G is also towards small cells, because with the millimeter wave coming in, because of the huge propagation loss or the path loss on the millimeter wave communication, the range of the cell is also restricted. So then obviously the cell range is also coming down. So small cells are the better choice for 5G also. So due to these constraints, with whatever the cancellation that we have achieved, it is possible to take this IBFT for practical realization for the small cell base stations. So with that, this IBFT has a very great potential to improve the required cellular throughput. I mean, that is what we have been working for. I mean, that is the use case scenario we started with, right? So it is possible to achieve whatever the throughput gain, close to double, because as we said, exactly the double requires complete mitigation of the self interference as well as the side link interference between the units. So any close somewhere around 1.9 or anything little over 1.9 times compared to the legacy, we should be happy with it. So, and in practical deployment scenarios in the near future, due to whatever the constraints and difficulties that we have discussed, hybrid kind of a network is more feasible, wherein only the base stations are full duplex capable, and the user equipments would continue to be half duplex devices. And the primary requirement for this hybrid network is an intelligent scheduling algorithm that optimizes the power, optimizes the frequency sharing, as well as reduces the self-interference and side link interference to improve the overall system capacity. Yeah, so this is the road ahead. We have made exciting progress in the last few years on this IBFD, but still there are many problems that are yet to be solved. Mainly, this SI to be cancelled over a wider band of frequency, because with 5G technology, the bandwidth of a component carrier is going all the way up to 1.2 gigahertz. In LTE, the maximum bandwidth of a cell is only 20 megahertz. This bandwidth is going all the way up to 1.2 gigahertz. 800 now, maybe it is going to become 1.2 gigahertz. So we should develop technologies to cancel the in self-interference on such a high bandwidth. Also, see, we have seen the practicability of IBFD for lower track TX power for small cell BS. We also developed technologies to accommodate macro cells and macro and micro cells, etc. And we have seen in the beginning that a single technology cannot solve all the problems, and we have to work in combination of technologies. MIMO is very prominent, so there are works already wherein the FD has to work in combination. The FD has to work in conjunction with the MIMO systems. So with MIMO system, what happens since we have many TX pads, right? We have to build a SIC circuit for every TX pad. So this number of SIC circuits in a system kind of scales quadratically. I mean, if you follow a very simplistic approach, and there has to be some innovation that to built in to minimize this, the number of SIC scaling units. Also, just like we have developed the systems with or people are working on developing systems with MIMO, it is also possible for FD technology to work with NOMO as well, and the problems associated with this kind of a joint work of NOMO and FD needs to be solved. And finally, yeah, we've seen the huge potential of this technology, and if you wanted to completely leverage upon the benefits of this, yeah, we need to have converged solutions both at the physical layer as well as at the MAC layer. So physical layer talks about physical layer works on minimizing the self-interference levels, and MAC works on innovating scheduling algorithm so that we can maximize the benefits of IBFD. Yeah, so this kind of comes to an end of my talk, just right on time. So are there any questions?
Thank you so much, Parthiban.
No
Big
problem.
clap for a nice talk. There is a question from Prasanna. So he was asking, is the channel characteristics the same for uplink and downlink?
We use what is called as a reciprocity theorem. We assume that using the reciprocity theorem, whatever the channel characteristics on uplink and downlink is assumed to be the same. Of course, it is not 100%. Even the TDD, the current TDD system uses the same approach. So we are just following this.
Okay. The next question is both rally, and question mark. Uplink can be handled with more base station capabilities. Downlink with limited mobile? Question mark.
I think he is asking if the channel characterization for uplink and downlink, if it both are assumed to be either Raytheon or rally fading, but as Parthiban answered, he has assumed those to be equal.
Yes.
The second question, limited mobility probably. Prasanna, if you're there, if you could explain that question, that would be helpful.
Oh, I think he's asking uplink can be handled with more base station capabilities, as in, I guess it can be resolved using more base station capabilities. So, what would you do for downlink with limited mobile? Limited compute resources in mobile. That's what Amod
That's
said.
right. That is the reason why we restrict. We don't want to do any changes in the GUI. We wanted to move all the complexities to the base station.
So you would do all the compute on the edge or something like that? Or?
No, base station will take care of all the computation. So we just whatever the today's mobiles are there, so that would work in the foreseeing this hybrid network also. All the complexities, additional computations, everything will be moved to the base station, the e-node piece.
Yeah, the understanding is that there would be a lot more user equipments or mobiles, and so trying to limit the most of the complexity to the base station and keeping the user equipment or our mobiles the way that they have been used all this time.
Okay.
I hope that answers your question, Prasanna.
Hi, Parthiban. This is Amrita. Wonderful presentation. So, just couple of questions I had. See, user equipments are typically our mobile phones, right? So, when we are using the frequency allocation algorithm, we are considering the parameters Dij's to be fixed, right?
Yeah.
So is that a valid assumption? If so, I mean, for what bouts of time can we, assume that these quantities are fixed and then run the proposed frequency allocation algorithm?
Sure. So let me answer this way. So whatever the any typical resource allocation algorithm that generally runs every TTI, meaning every scheduling interval, this allocation algorithms generally change. So if you take an LT system, 1 millisecond is the scheduling interval, which means that whatever the location information that we have obtained at the base station, as well as the power and frequency allocations that we have done for the UVs, have to be revisited every 1 millisecond time. So this 1 millisecond is going to further reduce if you go to 5G. This would even come down. So in a scheduling interval, we estimate these parameters, and accordingly we go and do all kind of frequency power allocation or the frequency share. And we take a decision at every TTI to decide whether the sharing is possible or not.
Okay, so
And
which translates to, if every 1 milliseconds the algorithm is going to run at the base station,
exactly.
right? And not only the algorithm, I mean, there has to be some user positioning algorithm which has to precede the frequency allocation algorithm, which calculates the DIs.
Exactly.
So
because even today's resource allocation algorithms are also running at TTI.
Right. But yeah, so here the additional overhead would be the user positioning algorithm in conjunction with the frequency allocation algorithm. I had another question. Why are we confining ourselves if we draw from the ideology of universal frequency reuse, where, the same frequency was used, say, after 6 adjoining cells, right? That was the
Yes.
ideology of the old school universal frequency reuse.
That's
Is there anything which in specific which is stopping us from, drawing from that ideology in this specific scenario? Why? That is, I think I missed the point. So if you could just...
Okay. Sure, ma'am. So basically what happens is, we are, the current presentation is confined to a cell. So within a cell, in a typical off-duplex kind of a system, there is no frequency reuse available. So, so every UE requires two independent frequencies for its own uplink and downlink. So that is the premises that we are working on. So within a cell, how well we can improve this frequency sharing so that the overall spectral efficiency of the cell can be improved. So that is the objective.
Wonderful.
So we, as of now,
maybe,
we are not working across cells.
Okay, maybe I think a trade-off kind of analysis with respect to, as you rightly pointed out, we are confining ourselves to a cell and then seeing what best we can do with respect to frequency reuse. So the additional overhead is, as you rightly told, we need to run some user positioning algorithm. So what is the trade-off when in comparison to opening it up to multiple adjoining cells and looking at the same frequency being reused? So I think that would give us a complete picture of the whole thing.
Yeah, I mean, definitely possible, ma'am, because then we have to bring in this multi-cell environment into consideration. Yeah, so then I'm sure this concept can be, extended, and more gain, spectral efficiency gain also would be possible. Yeah, definitely, this is something that is practically possible, I believe.
Okay, thank you so much. That answers all my queries. Thank you so much.
Thank you.
Thank you, Parthiban. Thank you, Amrita. Now, if there are no further questions, I'd like to invite Professor Das to speak a few lines about his new projects.
Thank you, Dr. Jaya. So nice of you for coordinating all these things and taking all the initiative in these directions. Before Parthiban's I start, I want to say about the Parthiban one more thing. He's very modest. He doesn't talk about himself. And I'm really happy to, we are all happy to work with him. And I cannot tell the name of the companies, but because of the recordings. But he is one of the pioneer in India in the DSP systems designs, and he was in the topmost mobile handsets modem design team of the which is used in one of the topmost mobile handsets. So you can guess what are that. So these are the very, very rare fit where any Indian engineer or scientist get to work in, sitting in India. So Parthiban has been working there and designing and making us IIITB proud. And from IIITB point of view, that is one thing. And in future, I always request Parthiban, when you are free, help us to design some of those DSP labs where our students will get benefited, where they can work like him. So thank you, Parthiban. Wonderful talk. We all enjoyed. And I will not take much time because we have crossed 3 o'clock marks, but I will take only a couple of minutes because today is only introductory to our project, which many people have heard about it. It is an advanced communication system IIIT Bangalore has got, and under the National NMICPS means National Mission on Interdisciplinary Cyber Physical System Projects and of DST. And myself, Professor Jyoshna, and other faculty members means I'm talking about Dr. Amrita, Dr. Vinod, and all those faculty members who have been involved in the communication networking. And also in future, if required, we'll also pull them in this. And this project has a completely focused areas with respect to advanced communication system. And in that regard, NMICPS technology, if you can look at, so this is an incubation hub, has been awarded rupees 150 crores from the government of India in IIITB in areas of this advanced communication system. And main focus is to not only to do only research. The government of India has changed this gear. Last 60 years, government of India has been doing only our research part in the academia, but they're telling academia to do research, but do the development and commercialization of the whatever you are coming out in the areas of advanced communication systems. So mainly that is a big change. That is the thing which I wanted to emphasize. So we will move towards the products from research to product. Mainly it will be addressed an R&D problem related to the 5G base station, because many extent it's a very complex problem, because you can look at Parthiban's presentation where he was only looking at the positioning of the mobile and finding out so how complex it is itself, one problems. But in 5G we have multiple problems, and it is becoming more and more complex due to the massive MIMOs and all, a different traffic type, different performances. So it's a pretty complex system. The more and more I read and going into it every day or every week, it is making me more and more convinced that it is a worth doing, but complex, very complex. And only you can understand only 3 big companies have end-to-end solution in this world. Only 3 big companies, end-to-end solutions. One is your Ericsson, other one is Huawei and Samsung. So these are has all the end-to-end. Other companies have solution, but they are beaten pieces. They are taking help of the other companies to integrate their products to do that. To come out, we come out with a new following a new architecture that is called Open Radio Access Networks, can help us to achieve 5G base station by distributed approach. What is a distributed approach? Say, as I have said just few seconds back, that is a very complex system end to end, because which I'll show you a picture why it is next slides. So to achieve this this distributed system means if we can do 60 to 70% here in our incubation hub, we can take other companies' products also to integrate into it in an open by this architecture called Open Radio Access Network, which has feasibility of doing that. But these 3 companies' product doesn't allow you to integrate any other third parties thing in their main base stations. So then other areas we are working on is that along with the 5G base station, reconfigurable intelligent surface, RIS we call it, and that is called smart surface also, and massive MIMO, network slicing, radar detection for UAV drones. These are the initial 5 areas we have thought of, but it may increase as we time proceed in the areas of advanced communications. So quickly, the traditional radio access network, RAN stands for radio access network architecture, is this. You can look at this. This is base station which you see on in front of you, and it has a transmitter, receivers, those antennas. Below that, there is RRH or RU, that is called remote radio head, or RU means radio unit. which is generally your transmitters, receivers, and also those analog and also those filters and all. And we use the baseband unit below that in the, it may be co-located one, which was, we might have seen 3G up to 3G and all. But later on, when 4G came in, then the people moved this BU to other locations. That is called cloud-based, centralized RAN to support cloud RAN deployments. You can look at this. So you can RRH and RU will be here, a lot of base stations, and they're connected by BBU. This BBU, which was co-located in the previous architecture, now it is being cloud-based kind of thing. So this the baseband unit, and each unit has a multiple stages of hardware, softwares to make you the communication. So, and mobile and the wireless and with mobility is a different based, completely different complex system. It's not easy to acquire and do the things. So from here we move to the new architecture, which is people are talking about, is that this RRH RRU unit is there. This is called front haul, and the BBU is connected to DU and CU. DU is called as a distributed unit and CU called centralized unit. The centralized units look after the higher layer protocols, mainly control protocols, and DU look at the MAC where the main data packets are being served and all. So these two units are connected to the BBU, and this is the backbone, the core networks connected. So we are, these architecture, what I wanted to show you is because these dotted lines, what you see, this connectivity and all those things, interfaces are generally proprietary. Proprietary means it belongs to a particular company. Those three companies, they own their own proprietary connectivity. So if you want to buy a base station, you have to buy complete thing from one person. You cannot buy from different person. They will not work interworking. So to break this one, the new architecture which we are talking about is called Open Radio Access Networks came in, where you can develop this physical layer part here or any of the other institutes, and you can work on the Mac in IIIT Bangalore. And this open front haul, this is the open interface, which has to be standardized and defined, and they can communicate with each other. So this proprietary thing which you saw in the previous slide of connectivity between the different units here will be taken care by the open source or open interfaces. These are has to be standardized. So then what will happen if any of these units, one of these IITs develop this one, say physical layer, or IIIT Bangalore develop the part of the physical layer, they integrate it. A Mac is developed by somebody, they can be integrated. And above that, there are so many interesting things you can see at here in the top. Orchestration, automation, these are called the brain of the whole communications. So there will be another interface connected to RAN intelligent control. So a lot of ML AI based interfaces will be there, which will be taking the decision making, and also the multi-RAT CUs and all those things. You can see here centralized units. So if you see from top to bottom, from here to here, there are multiple units, multiple open interfaces. These are all open interfaces which will be standardized and which can help us to make the 5G base station much faster way. But there are a lot of challenges in this. It's not so easy. I have been talking to many people in the weekdays and weekends and finding out the challenges, noting down. So it's not easy because of the who is developing what and how to integrate them, how to standardize them, and moreover that after integration, giving end-to-end performances like delays, throughput with respect to 5G's requirements of the standards. It's not an easy task. It's a epic task in front of us. So one problem I only said in brief. With the interest of time, I'm stopping at here. One day we will give you a complete detailed design and architecture ones, and other kind of intelligent surface and all kind of problems. So thanking you again and giving me an opportunity to speak. And I stop at here and looking forward to all of you, your wishes and supports in the future to work on these projects.
Thank you so much, everybody. It's been a wonderful talk, and great to know the things that IIITB is involved in the larger context. So, thank you, everybody. We'll